Hello everyone and welcome back to Nunley Math. I'm Aaron Nunley. Thank you so much for joining us here today as we talk about scientific notation. I normally talk about scientific notation at the end of our exponents unit because it does rely very heavily on some of the information that we learn in our exponent units, but it is a very, what I describe as a niche topic in math, meaning it has a very specific purpose and a very specific use. A lot of the things that we do in mathematics apply in a variety of different areas, but scientific notation, as I'm sure you probably have already guessed, is a way of writing numbers that is used a lot within the scientific community. Because it relates to numbers that are very large and very small, and it deals with how we can write those very large and very small numbers in a convenient way. So let's go ahead and get rolling. I want you to think about something. If I have the number 5, of course that has a value of 5. But if I were to take that 5 and multiply it by 10, it now has a value of, I'm sure you guessed, 50. And if I were to take that 5 and multiply it by 10 and multiply it by 10 again, what value would it have? Well, hopefully you realize it has a value of 500. And if I take a 5 and multiply it by 3 tens, it has a value of 5,000. And a 5 times 4 tens would have a value of 50,000. And I want us to pause and think about this for just a second, because most of us probably do this fairly instinctively based on some things that we learned back when we were in elementary school. Now, ordinarily we don't write this decimal point here, but I included it because I wanted us to take a look at what happens to this decimal point, or to the place value of this number as I multiply by tens. Take a look. Here we had 5 with a decimal right next to it. After I multiplied by a 10, I have a 5, 0, then a decimal, 5, 0, 0, then a decimal, 5, 0, 0, 0, then a decimal, and 5, 0, 0, 0, 0, and a decimal. What seems to be happening to this decimal as time is going on? Or I should say, as we multiply by extra tens. Well, hopefully what you've realized is that every time I multiply by a 10, my decimal point moves to the right. Or in other words, the place value of this 5 gets larger. This was 5 ones, this is 5 tens. Or if I multiply by 2 tens, times 10 times 10, my decimal moves 2 places. Or this 5 goes from being worth 5 to being worth 50 to being worth 5 100s, and 5 1000s, and 5 10,000s. You see, multiplying by 10 takes this 5 and it changes its value by moving it to a different place value location. Or another way to think of that is to say this. Every time I multiply by a 10, it has the effect of moving the decimal one place to the right. One place to the right, 2 tens would be 2 places to the right, 3 tens is 3 places to the right, and 4 tens is 4 places to the right. Now, I can do something similar to that with dividing by 10. If I take 5 divided by 10, a lot of us may or may not know what that is off the top of our head, but I do want to remind you that it is 0.5, and that dividing by 10 is the same as multiplying by the reciprocal. Remember, division is the same as multiplying by the reciprocal, so 5 divided by 10 is the same as 5 times 1/10. If I do that, you probably know that 5 divided by 10 is 5 tenths, or 1/2. I've given it to you in decimal form. But what happens if I multiply by my 5 by 1/10 and then by 1/10 again? Remember, you could think of this as being a 5 over 1 if it's more convenient for you, and then you could just multiply across the fractions. 5 times 1 is 5. 1 times 10 is 100. This is going to be 5 hundredths. 5 hundredths. That is in fraction form. This would be 5 over 100, which in decimal form would be 5 hundredths. And I can continue repeating this. This would be 5 times 1 times 1 times 1, which is 5 1000ths. Or in decimal form, 0.005, and I'm sure you can figure out what's going to happen next. Notice that every time I divide by 10, every time I divide by 10 or multiply by a tenth, because these are the same thing, every time I do that, that decimal is going to move one place to the left. This was worth 5 wholes, now it's worth 5 tenths. And when I do 2 tens, the decimal moves 2 places to the left and I get 5 hundredths. And if I do it 3 times 5 thousandths, and if I do it 4 times, I get 5 10,000ths. Every time we divide by 10, it has the effect of moving the decimal one place to the left. You might, if you're writing these notes down, also say times 1/10, because dividing by 10 and multiplying by 1/10 are the same thing. Now, the purpose of this slide is just to point out that we can begin to write very, very large numbers and very, very small numbers by using some number times however many tens we want in order to put it into the place value we like. Consider this. If I have 11 million, 11 million is just 1,100,000 times 10. If I have 11 million, that could be 110,000 times 2 tens. Remember, this 10 would move this decimal over one place and make it match. Since I have 2 tens here, I would move my decimal 2 places and it would match. 11 million can be written a lot of different ways, depending on how many tens I would like to multiply by. Every one of these expressions means the exact same value or the exact same number. And I can even go one step further, and I can take these and I can write them using an exponent to express the number of tens. 11 million is 1,100,000 times a 10. Or I could say it's 110,000 times 2 tens. See, there's 1, 2. Or 11,000 times 3 tens. Or 1,100 times 4 tens. In fact, I can go through a lot of different ways to write that same exact number. What's cool about this is if I look at how much work it is to write 11 million, and I look over here and see how much space these numbers take up, you'll notice that as I increase the number of tens I'm using, I have a lot less to write in regards to this number. This number is getting shorter and shorter and shorter. It actually is at its shortest point either here, here, or here, right? Consider it the other way around. If I gave you a tiny, tiny number, like, see, this is tenths, hundredths, thousands, 10,000s, 100,000s, millions, 10 millions. This is 7 100,000,000s. That's 7 in my numerator and 100 million in my denominator. That takes up a lot of space to write. But keep in mind that every time I multiply by 1/10, I move my decimal. So this has 1, 2, 3, 4, 5, 6, 7 decimals. If I wrote it with 6 decimals, I know that this 1/10 would move that decimal one more place, making these the exact same value. I can change the way the number looks by using times tens or divided by tens or times 1/10 to move this decimal over. Instead of having this 7 way, way over here and then all of these zeros, I could actually write it so the 7 is by itself times a bunch of 1/10 or divided by a bunch of tens. Now that doesn't look shorter, but if I were to use exponents, keep in mind that in our exponent unit we learned that 1/10 is 10 to the negative first power. This would be times 1/10 to the second, or using negative exponents, 10 to the negative second, 10 to the negative third, 10 to the negative fourth, fifth, sixth, seventh, and eighth. All of these values over here on the right-hand side of the screen are shortcut ways to write all of these numbers that are over here. Wow, that's a terrible arrow. All of those numbers that are over there on the left-hand side of the screen. That's what scientific notation does, is it allows us to take weird numbers with lots and lots of zeros in and try and find a shorter way to write them so they take up less space and they take up less time to write. Now, why would we want to do that? Well, most of the time people don't want to do that. But in science class, and in the scientific community. Sometimes they run into issues where they're dealing with really, really big numbers. For example, the mass of the Earth in kilograms. This is thousands, millions, billions, trillions, quadrillions, quintillions, sextillions. The mass of the Earth is 5 septillion, 972 sextillion kilograms. And if I'm a scientist and I'm trying to do some math, for example, trying to figure out what 50 Earths weigh or 70 Earths, imagine trying to go through and multiply all of this by 70. What's weird is most of my time wouldn't actually be spent doing any mathematical work. Most of the time I'd just be writing down a bunch of zeros. 0 times all of this and 7 times all. It's a lot of unnecessary work. So what scientists want to do is they want to find ways to avoid having to do that. Or consider this. This is the diameter of the Milky Way galaxy. This is, let's see, millions, billions, 621 trillion, 371 billion miles across. That's a big number to have to work with. Or the speed of light, 300 billion millimeters per second. Or the distance from our sun to the next closest galaxy. Let's see, this is millions, billions, trillions. This is 662 quadrillions. When scientists work with very, very large numbers, it's easy to get lost in all those zeros. We need a better way to write that. Scientific notation allows us to write numbers that are very large or very small in a way that's easier to work with. This right here is the formal definition of scientific notation. The number is written so that it is the product of a number between 1 and 10 raised to a certain exponent or power. We're going to have a number times 10 to an exponent, and the number we use is always going to be between 1 and 10. Let's play with that for just a minute. Consider this. A boulder in Colorado weighs 52,000 pounds. Let's write that in scientific notation. 52,000 pounds. Now, usually you would see that as 52,000. This is called standard form. This is 5.2 times 10,000. I know this because if I want my decimal to be here, I would have to do 5.2 times 10 to get 52, times another 10 to get 520, times another 10 to get 5,200, times another 10 to get 52,000. 5.2 is a number between 1 and 10, but this number is not big enough. I need to multiply it by a bunch of 10s to make it equal 52,000. In this case, I moved that decimal. I'm going to have to move that decimal 1, 2, 3, 4 places, which means I'm going to need to multiply it by a 10 4 times. We have standard form, how you're used to seeing it, expanded form, where we say, you know what, I have a number between 1 and 10 times some 10 to a power, some big number, and then in scientific notation, I take the number between 1 and 10, and I say how many 10s it has to be multiplied by. It's a little shorter. Here's another one. If I have 52,000, I could take a shortcut way rather than going through expanded form, and I could just say, hey, I know I need my decimal to be here. I know it has to be here because I have to have a number between 1 and 10. 5,200 is not between 1 and 10. 520 is not between 1 and 10. 52 is not between 1 and 10. I know my decimal has to go here. So what I can do is just count how many places that decimal has to go. 1, 2, 3, 4. I know that if I have a 5.2, I'm going to need to use 1, 2, 3, 4 10s in order to turn it into 52,000. So the scientific notation would be 5.2 times 10 to the 4th. See how that works? On this slide, I'm just going to give you some numbers and ask you to write them in scientific notation. My suggestion to you is that you pause my video and you try this one first, then you restart the video and listen to my explanation and see if yours matches. If you feel pretty confident, you can fast forward through my explanation and just check the answer. But I would do these one at a time. Do this one, watch the video. Do the next one, watch the video, and we'll see how it goes. Here's what I know. I know that 48,000 is too big to be called scientific notation. I need a number that's between 1 and 10. So I need my decimal to go right here between the 4 and the 8. It starts here. I need it to be between the 4 and the 8. That's 1, 2, 3, 4 places away, which means to turn a 4.8 into 48,000, I'm going to need to keep the 4.8 and use 1, 2, 3, 4 tens. This is 10 to the 4th. How about this one? 781 million. Your decimal starts right here. You need to put it here to get a number between 1 and 10. That means you're going to need to move that decimal 1, 2, 3, 4, 5, 6, 7, 8 places. 8 places. You're going to have to take a 7.81 and multiply it by 8 tens in order to make it equal to this number right here. 7.81 times 1 10 would be 78.1, times 2 tens would be 781, and so on and so forth. Here's one more. Your decimal starts off right here. You need it to be between the 2 and the 6 because 2.6 is between 1 and 10. That's a movement of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 different places. So you're going to need 2.63 times 10 to the 14th. If you want to turn this into this number, you're going to have to multiply by 10 14 times. That's not too bad, right? Let's try it the other way around. Suppose you are given something in scientific notation and you're asked to put it into standard form. You're asked to put it into standard form. Well, you start with 3.77. And this says you're going to multiply by 6 tens. If I multiply by 1 10, that's going to make it 37.7. 2 tens would be 377. 3 tens is going to be 3,770. 4 tens, 5 tens. The number you're going to end up with, 6 tens, there it is, sorry. The number you're going to end up with is 3,770,000. You've moved your decimal 1, 2, 3, 4, 5, 6 because you're multiplying by 6 tens. Can you do another one? Pause the video, try this one on your own. I'm going to assume you've already done that, and I'm going to keep going. I need to take that 8.63 and I need to multiply it by 3 tens. That means my decimal is going to move 3 places. 1, 2, and 3. I'm going to fill in that blank with a 0. Multiplying by 10 made it 86. A second 10 made it 868. And the third 10 makes it 8,680. There's your solution. It's not bad, right? One more. Again, try this on your own. I want to take the 4.9. I need to multiply it by 14 tens. That's going to move my decimal once around the 9 and then 13 more times. So that I end up with 490 trillion. 490 trillion. Now, scientific notation usually doesn't make a whole lot of sense if my numbers are fairly small, like the 48,000. But when I start dealing with numbers like 490 trillion, it's a lot easier to just deal with the 4.9 than it is to have to worry about all of these zeros. Okay? Here's another example using some small numbers. A skin cell has a diameter of 0.00003 meters. I want to put this in scientific notation. It's given to us in standard form. Here's what we know. Every time I divide by a 10 or I multiply by a 1/10, my decimal is going to move, okay? So I want my number to be a number between 1 and 10. I want this to be a 3. But in order for it to be a 3, I'm going to have to multiply this by 1/100,000th. In fact, if I read this, this says 3 tenths, hundredths, thousandths, 10,000ths. This is 3/100,000ths. That's expanded form. And if I wanted to do this in scientific notation, well, this is going to be 3 times 10 to the negative 5th. You'll remember from our exponent lesson, I actually have a little pop-up that's not showing up here. You'll remember from our exponent lesson that this would be 3 times 10 to the 1/10th, 3 times 1/10th to the 5th, and then the negative says to flip it over. I'm sure that'll pop up at a really inconvenient time somewhere else on the slide. I need to fix that. Consider this. In scientific notation, it's 0.00, should I say, in standard form, it's 0.00003. If I would like for this to be in scientific notation, I actually have to move that decimal 5 times. Once around the 3, once around the 0, 0, 0, 0. This is a movement of 5 places. But since I'm trying to take this 3 and make it smaller, I'm not multiplying by 10, I'm rather dividing by 5 tens. Was that confusing? I think it's a little more confusing that way. There's the random rogue slide pop-ups that didn't appear when I wanted them to. I'll have to go back and fix those later. Let's try a couple of these. This is the last slide. I've got a really tiny number. I don't want to deal with all those zeros, so I want this to be in scientific notation. I need my decimal to be between the 1 and the 5, because 1.5 is between 1 and 10. So I count over how many decimal moves that is. 1, 2, 3, 4, 5, 6. That is 7 movements of my decimal point. 7 movements of my decimal point. So I'm going to take that 1.5 and I'm going to multiply it by a bunch of 1/10ths. I'm going to multiply it by 7 1/10ths, or -7 tenths. Did I say that right? Instead of multiplying by 10, I want to divide by 10, which is why I use the negative exponent. The negative exponent says use the reciprocal, which would be the same as division. Some people often get in trouble or end up with difficulties because they can't remember whether to make this a positive or a negative number. I always look at this and compare it to the other number. Do I want this to get bigger or smaller? Well, I want to take this 1.5 and turn it into something tiny. Therefore, I need to divide by 10. That's how I know it's a -7. Once again, I would pause the video. Try this on your own. Restart the video to check your work. 0.00386. That's tenths, hundredths, thousandths, 10 thousandths, 100 thousandths. This is 386 hundred thousandths. I'm going to assume you've already worked this out with the video paused if you plan to do that. I look at this and I say, hey, you know what? I need that decimal to be between the 3 and the 8 because I have to have a number between 1 and 10. That is a movement of 3 places. So I have 3.86. I'm actually going to be dividing by 3 tens, so I use 10 to the -3rd. 10 to the -3rd. One more. Pause the video, try this on your own. Don't let the negative sign throw you off. You're still going to do the exact same thing. You want that decimal to be between the 6 and the 3. That's a movement of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's a movement of 11 places. So I need to take that, don't forget your negative sign, -6.34, and I need to multiply it by 11 1/10ths, or 10 to the -11th power. The last thing you might have to do is you might have to take something that's already in scientific notation and write it in standard form. This actually is much easier because we can already see that we're going to need to move that decimal 7 places, and we're going to take that 8 and we want it to be smaller. So 8.33, I'm going to take it and I'm going to divide by tens. That moves the decimal to the left. 1, 2, 3, 4, 5, 6, 7. That's what we want to end up with. We need 6 zeros, 8, 3, 3. This is standard form. This is scientific notation. Don't be afraid or ashamed on your paper to write these arrows out. A lot of students get a little overconfident. They don't do that. They end up miscounting the number of zeros they need. Be very, very careful. I'd suggest pausing the video and trying this on your own. I'm going to assume you've already done that. I take my 2.74. I know I need to move my decimal twice, and I know I'm dividing by 10, so I want to take this and make it smaller. 0.2, 0.02. There's your answer. Last one. I have my 3.716. I want to move that decimal 12 places, and I'm going to use that to make it smaller. This is going to be smaller than 3. 1, 2, I'm not going to count them all because it takes forever. You can pause the video if you need a second to write that down. And there's your answer. 0.0000000003716. Hopefully this has been helpful for you as well as useful. Again, take your time with this. Think about what those negative exponents represent when you're trying to decide what direction your decimal needs to go. Make sure you write out your processes. Most of the mistakes here are typically just miscounting the number of zeros and putting their decimal in the wrong spot. As always, I do appreciate you taking the time to join us here today. I do wish you all the very, very best of luck. You guys take care of yourselves, all right? Bye-bye.